Thank you for the introduction. And I would like to thank the organizers for the invitation to this nice congress. And today I'm talking about the strong slope conjecture for knots obtained by some elementary operations on knots, including Mazur pattern satellite knots. And this is joint work with Ken Baker and Toshie Takata. So, so we are interested in some relationship between Carrad-Jones polynomial denoted by J, Kn of Q, and some geometry or topology of knots. And as a relation to geometry, there is a famous conjecture called volume conjecture due to Kashaev, Jun Murakami, and Hitoshi Murakami, which suggests that relation between Carrad-Jones polynomial and the hyperbolic volume of hyperbolic knots, more generally, simplicial volume of knots. And today we are interested in a topological part. So as a relation to topology, so, Galfardis proposed somewhat novel conjecture called slope conjecture. And later, Carpagiani and Toran refine strong slope conjecture to strong slope conjectures, and which suggests a relationship between Carrad-Jones polynomial and essential surface in the exterior of the knots. So Carrad-Jones polynomial of a knot K is a sequence of Laurent polynomials L, K, N of Q, and N corresponds to Carrad. And here we use unnormalized Carrad-Jones polynomial. And here unnormalized means that usually Carrad-Jones polynomial of the trivial knot is 1 here, but we use the unnormalized version so that the Carrad-Jones polynomial of the unknot is just a Q integer, something like this. Okay. And now we look at a concrete example of the torrefied, right-hand torrefied knot. And according to N, we have a sequence of Carrad-Jones polynomial like this. And so now we look at the maximal degree of the Carrad-Jones polynomial. And at the first glance, they have no relation. However, the maximal degrees satisfy the following quadratic polynomial 3 over 2 n squared minus 3 over 2. And in general, Galfardis and Ray proves the following interesting phenomenon. So for any knot K, there is a constant n0 such that if n is greater than or equal to n0, then the maximal degree of the Carrad-Jones polynomial is a quadratic quasi-polynomial. And here, quasi-polynomial means polynomial whose coefficients are not constant, maybe periodic functions. So here is a situation. So in the left picture, draw the usual quadratic polynomial. On the other hand, in the right side, so green point is unstable range. And so for small n, we don't have information about the maximal degree. But for sufficiently large n, we have a quadratic, the maximal degree becomes a quadratic quasi-polynomials. And in this picture, the period is 2. So for instance, if n is odd, then the maximal values take maximal degree take values corresponding to red points. And if n is even, then the maximal degree takes value corresponding to blue points. This is a quadratic quasi-polynomial. And based on this fact, Galfardis defines the Jones slopes as follows. So a rational number P over Q is a Jones slope if there is some natural number n such that P over Q is 4 times the coefficients of the quadratic term of the maximal degree. And we denote the set of the Jones slope by Js of k, which consists of 4 times the coefficients of the quadratic term of the maximum degree. And as I said, A of n is a periodic function. So the cardinality of this Jones slope set depends on the period of the A of n. And actually, in all known, previously known examples, the coefficients of the quadratic term has period 1. So namely, A of n is constant. Okay. So we introduced the Jones slope and another slope. So this is a more familiar one. So boundary slopes. So we denote the exterior of K by E of K and choose preferred meridian longitude pair mu lambda of K. And then we say that rational number or infinity corresponding to the meridian P over Q is a boundary slope of K if there is an essential, meaning compact, orientable, incompressible, and boundary compressible surface F in the exterior of K, whose boundary component represents P times meridian plus Q times longitude. And the set of the boundary slope is denoted by PS of K. And this set is always finite by Hatcher's finiteness theorem. And since incompressible Seifert surface has slope 0, so this set always contains 0. And furthermore, Kara-Sharen shows that any knot has a non-zero boundary slope. Okay. So now we explain what is a slope conjecture due to Galfaris. So as I explained, we have a sequence of Colored-Jones polynomial like this, and for sufficiently large n, the maximum degree of the Colored-Jones polynomial is a quadratic quasi-polynomial, written by A of n square plus B of n plus G of n, and coefficients are in general periodic functions. And pick Jones slope P over Q. Then by definition, we have an integer n such that the P over Q is 4 times the coefficients of the quadratic term of the maximal degree. And then slope conjecture asserts that there is an essential surface, Fn, whose boundary slope is exactly the Jones slope. Okay. Sorry. Okay. Okay, so later, Carfagiani and Toran strengthened the slope conjecture in the following sense. So again, we have a sequence of the Colored-Jones polynomial here, and for sufficiently large n, the maximal degree is a quadratic quasi-polynomial, and so the slope conjecture asserts that there is an essential surface whose boundary slope is the Jones slope, which is 4 times the coefficients of the quadratic term of the maximum degree. And now, Carfagiani and Toran takes care of the linear term of the maximum degree. And then this essential surface Fn satisfies the following equations. So Euler characteristic of Fn over the number of boundary components times the denominator of the Jones slope equals 2 times the coefficients of the linear term of the maximum degree. So the strong slope conjecture says that the maximum degree of the Colored-Jones polynomial has information about the essential surface. In particular, so the quadratic term has an information about the boundary slope. And furthermore, the linear term has an information of the topology of the essential surface. And at the beginning, honestly, I didn't believe this novel conjecture, but so we present some, we take a closer look at some examples. So here is the simplest example, the right-hand trefoil knot. Then the maximum degree of the Carrad-Jones polynomial is 3 over 2n squared minus 3 over 2. So by definition, the Jones slope consists of a single element, 4 times the coefficients of the quadratic term, 3 over 2. So 6 is the Jones slope. And then it is obviously we have a cabling annulus, whose boundary slope is 2 times 3 equals 6. So this is the required essential surface. And furthermore, the Euler characteristic of F1 over the number of boundary components times the denominator equals 0, and which can be written as 2 times 0 equals 2 times the coefficients of the linear term, this one. So the right-hand trefoil knot satisfies the slope conjecture. So this is due to Galfardis. And the second one is another famous example for figure 8 knot due to Futta, Calfagiani, and Purcell. And in this case, the maximum degree of the Carrad-Jones polynomial is n squared minus 1/2 n minus 1. And again, this is the usual quadratic polynomial rather than Kazi polynomial. And in this case, the Jones slope is 4 times 1, so it is 4. And so we need to find an essential surface whose boundary slope is 4. But it is well known that figure 8 knot has an essential exterior of the figure 8 knot has an essential surface with boundary slope 4. So this is the required essential surface, and which satisfies the following. So the Euler characteristic of F1 over the boundary, the number of boundary components times denominator equals so minus 2 over 2, so which is minus 1, and writing minus 1 as 2 times minus 1/2. And since the linear term is minus 1/2, so this is 2 times the coefficients of the linear term of the maximum degree. So again, the figure 8 knot satisfies the strong slope conjecture. And so maybe this is just an accidental coincidence, but the next one is more forces us to believe the strong slope conjecture. So Galfardis present the example of minus 237 pretzel knot. And the maximum degree of the Carrad-Jones polynomial of minus 237 pretzel knot is 37 over 8 n squared minus 1/4 n plus epsilon of n. And here, epsilon of n has period 4. So this is not a usual quadratic polynomial. This is the quadratic quasi-polynomial of period 4. But the quadratic term and the linear term is just constant. And then the Jones slope is 4 times 37 over 8, so 37 over 2. And so we need to find again some essential surface whose boundary slope is 37 over 2. And it is also known that we have an essential twice punctured torus with boundary slope 37 over 2. And this essential surface shows that 37 over 2 surgery on minus 237 pretzel knot is a toroidal manifold. And this is a member of the Mario's half integral toroidal surgeries. Okay. And so considering the Euler characteristics, and then the Euler characteristic over the number of boundary components times denominator equals minus 2 over 2 times 2 equals minus 1/2, and which is also written as 2 times minus 1/4. And this is exactly the coefficients of the linear term of the maximum degree. So this not satisfies the strong slope conjecture. So in some sense, these phenomena doesn't look like accidental coincidence. And okay, so here is a collection of knots which are known to satisfy the strong slope conjecture. So torus knots and alternating knots are known to satisfy the strong slope conjecture due to Galafardis by himself. And actually, Galafardis didn't show the strong slope conjecture because he only considers a slope conjecture at that time. But his computation enables us to check these knots also satisfy the strong slope conjecture. And later, Futta, Carfagiani, and Parcel extend the class of knots which satisfy the slope conjecture to include B-adequate knots, and which include adequate knots because adequate knots are A-B adequate knots. And this also include alternating knots. And knots up to 9 crossings due to Galafardis, Josh Howey, and Carfagiani, and Toran, and certain families of pretzel knots with 3 branches, rational tangles, by Liu Shanli and Van der Been, and certain families of Montesinos knots due to Galafardis, Li, Van der Been, and Ren Yang Q, and Carfagiani Toran studies about the cables of certain knots. Okay. So, so here we consider some elementary operations, something like connected sums and cablings and Whitehead doubles. These appears in the previous talk. And so cable knot is a satellite knot with the pattern like this, zero bridge plate torus knots, insert the torus, and Whitehead double is satellite knots built up by this pattern. And so here is a major pattern satellite knot. So we consider the pattern depicted in this picture. So similar to Whitehead double, but Whitehead ring, but laps more than one, another one lap here. And so our main result, our result can be stated as follows. So any knot obtained by a finite sequence of taking connected sums, cables, Whitehead doubles, and major pattern satellites of torus knots over B-adequate knots satisfies the strong slope conjecture. And here is a schematic picture, a satellite diagram. And this means that we start with a B-adequate knot and taking cables and taking Whitehead doubles and connect some with another adequate knots and taking cables and so on. And the theorem says that any knot obtained in this manner always satisfies the strong slope conjecture. And restricting cablings and connected sums and on torus knots, then we obtain any graph knot. So this implies that any graph knot satisfies the strong slope conjecture. And so here is just a brief sketch of the proof. And as a first step, we describe the Colored-Jones polynomials of the, for instance, major pattern satellite knot M of K using the Colored-Jones polynomial of the companion knot K. And in this computation, we apply the graphical calculus of Nussbaum and Vogel. And as a second step, we need to determine the maximum degree of the Colored-Jones polynomial. And so in this step, a difficulty occurs because the maximum degree of the Colored-Jones polynomials becomes a quadratic polynomial only for sufficiently large n. So we don't have any information for small n, and difficulty, we have such a difficulty. And here is a simplest situation. So namely, the maximum degree is a usual quadratic polynomial. So each coefficient is constant. This we present just a simplest situation. And in this case, the maximum degree of the Mazur pattern satellite has this form. Okay. And the last step, we find an essential surface. And so write the maximum degree of the Carl-Jones polynomial of the companion node like this. Then, as the previous proposition said that for if A is positive, then the maximum degree of the Carl-Jones polynomial of Mazur pattern satellite has this form. So we decompose the exterior of the Mazur pattern satellite node like this. Here is exterior of the Mazur pattern satellite node in the companion solid torus. Yellow piece is the exterior of the Mazur pattern satellite node of the companion solid torus. And this suggests that the boundary slope of E of K, the companion, is 4 times A. And on the other hand, the boundary slope of the Mazur pattern satellite is 4 times 9A equals 36 times A. And since K satisfies, the companion node K satisfies the strong slope conjecture, we have an essential surface in this green curve. This green curve indicates the essential surface whose boundary slope is 4 times A. So we need to find an essential surface in X, which has a boundary slope 4 times A on the boundary of EK and 36 times A on the boundary of the Mazur pattern satellite node. Okay, but we observe that X is homeomorphic to the exterior of the two-bridge link 5/14. So we may, thanks to Floyd-Hatcher and Host-Shanahan, we have a good machinery about to construct an essential surface and apply Floyd-Hatcher and Host-Shanahan to obtain a desired essential surface from the weighted minimal edge path in something. So weighted or parameterized Farey diagrams. And we list up minimal edge path from 1/0 to 1/14. And we have several minimal edge paths. And finally, this is a good candidate. And each segment corresponding to the branch, the model of branch surface. And according to following this minimal edge path, we can build a branch surface like that, like stacking them. And the weight enables us to obtain some essential surface connecting the which has a boundary slope 4 times A and 36 times A. And this shows that, for instance, Mazur pattern satellite node also satisfies the strong slope conjecture whenever the companion node does. So I would like to stop here. Thank you very much.
Sorry, I forgot to unmute there. Thank you very much.
Thank you very much.
Are there questions?
I have a question. Kimihiko, you had a whole list of sort of operations that you're allowed to do. Do you know anything about whether you can get all knots that way? I mean, those are that many operations.
Many. So you mean that
You know,
any operations?
and connect summing and so forth.
Yeah.
Is there obstructions to getting certain knots that way, or is that actually maybe?
I'm not sure, but so actually we can apply Freud hatchers for more satellite knots, but in general it is difficult to compute the Collatz-Jones polynomials and difficult to determine the maximum degrees.
Okay.
Yeah.
Okay.
Yeah, but a knot can have more than one Jones slopes.
As so far, we have no examples. So in any examples, Jones slope is a single element. Jones set consists of a single element because the coefficient of the quadratic term is constant so far.
Hmm.
But theoretically,
So far,
Galfaldi shows that only periodic functions. So there is no examples.
No.
And so we are interested in what is the Jones surface. What kind of surface Jones slope, Jones, Collatz-Jones polynomial knows.
Uh-huh.
Other comments?
Just a follow-up on Jennifer's question. So what hyperbolic knots has this been verified to other than B adequate knots?
So sorry, Yoav?
Yes, so
Yoav.
You said it's been verified for B future Kalfajani, exactly. What other, your operation do not give hyperbolic knots, right? Connect summing and so on, satellites.
Yeah. So you mean that we assume that so this kind?
No, so I'm just asking, are there any other hyperbolic knots for which this?
Possibly, but so actually to determine the maximum degree, we need technical assumptions. And so at least torus knots and B adequate knot satisfies this. But for instance, maybe some Montesinos knot does not satisfy the technical conditions, and we cannot apply so far for Montesinos knots.
And so the conjecture would be still open there?
Yeah, for instance, Mazur pattern satellites of some Montesinos knot satisfy the slope conjecture or not. Yeah, because of the technical conditions to determine the maximum degree. Yeah.
Other questions? Okay, let's reconvene then in about 10 minutes, 40 minutes past the hour.